So, so welcome everyone. Today we're greatly honored to have Dr. Andrew Gelman to give a talk for us. Dr. Gelman is a professor of statistics and political science at Columbia University, and he's a very prolific scholar, and he has written several high-impact books, including what I know of Bayesian data analysis and data analysis using regression and multi-level hierarchical model. He also has several other books, and Dr. Gelman has received the Outstanding Statistical Application Award for 3 times from the American Statistical Association, the Best Award for Best Article published in American Political Science Review, and the COPS Award, which was awarded to the outstanding statisticians under the age of 40. And Dr. Gelman has done a lot of research covering a wide range of topics, including the topic today, why it is rational to vote and how can we predict presidential election results. So without further ado, let's welcome Dr. Gelman to give us the exciting talk today.
Okay, I don't think that why it was rational to vote was on the agenda, but I'll tell you about it because it sometimes does come up. There's been some literature on the probability of your vote being decisive. Actually, some pretty bad literature on the topic. The most, if you have a little statistical training, or maybe I should say too much statistical training, your first thought on estimating the probability of, well, first let me say your vote will be decisive in the election if the election is tied or within 1 vote. The natural way to estimate that would be using a binomial distribution model. So if everybody is flipping a coin to decide how to vote, then you can figure out the probability that you have exactly 50-50 split. Which of course isn't quite right, because if you look at actual elections, they're not split within a binomial distribution of 50-50. Then people will do things like say, well, the election was 52-48. So what's the probability of an exact split if each person is spinning a spinner with a 52% chance of heads and a 48% chance of tails? What's the probability of an equal split that way? And that result will be wrong also, because people are not voting at random. Some people are much more likely to vote for one party, and some people are much more likely to vote for the other. So it turns out that if you want to estimate the probability of your vote being decisive, the most effective way of estimating this is empirically. We can, for example, use a statistical model to estimate the vote proportion of candidates within each state. I'll talk about that in a little bit. Given the estimate of the vote proportion in each state, you can estimate whether the vote proportion is sufficiently close to 50-50. Under a continuity assumption, this is pretty much the same as estimating the probability the election is within 1,000 votes and then dividing that by 1,000. We're estimating the probability the election is within 10,000 votes and dividing that probability by 10,000. You'll get about the right answer. You'll get a number. Well, in California, the probability of your vote being decisive in the presidential election in California is basically 0, because California is not at all close. But in a swing state, such as Arizona, the probability your vote is decisive in the national election is on the order of 1 in 10 million. For your vote in Arizona to be decisive, Arizona has to be tied or within 1 vote, and then Arizona's electoral votes need to be necessary for the winning candidate to have a winning electoral coalition. So if the probability that your vote is decisive is 1 in 10 million, you want to estimate whether it's rational to vote, people have done a simple calculation. So the utility of voting is the probability of voting times the difference of utilities of whether your preferred candidate wins or loses. So for example, if you prefer a certain candidate because you think they would lower your taxes by $3,000, and the chance of your vote being decisive is 1 in 10 million, then you get 3,000 divided by 10 million is your expected utility from voting, which is some number less than 1 cent, which is led various political scientists to claim that voting is irrational because it certainly takes more than 1 cent worth of effort to go out and vote. Even the cost of the gas in your car alone is more than 1 cent. Yet people vote anyway. So that's been called the paradox of voting. Now there are various resolutions to this paradox of voting. One possible resolution is that people vote just because they want to, because they derive enjoyment out of voting, or because it makes them feel less guilty after the election is over. It's not completely clear that's not really enough of an explanation to vote, partly because there is some evidence that people take their vote seriously. And in addition, voter turnout is higher in close elections, tends to be higher in more important elections, which wouldn't quite fit the story of people just voting because they feel that they're supposed to. There is actually a rational reason to vote, though, and it goes as follows, that you might very well feel that your preferred candidate is not, you don't vote for a candidate because he'll give you a $3,000 tax cut. You vote for your candidate because you think he'll bring peace and prosperity to the country and even maybe to the world. You might be concerned about long-term issues such as economic competitiveness, climate change, immigration, abortion, all sorts of issues which you feel, some of which you can put a dollar value on and some which you can't, but issues that you feel will affect millions of people. People vote based on abortion, even if they're not planning to have any abortions themselves, because the issue still seems important to them. Now, suppose that you feel your candidate will improve the utility of people, will make people happier by, let's say, the equivalent of $1,000 each. $1,000 seems, it's not a trivial amount of money, but it doesn't seem implausible given all the decisions that the president can make. And we've seen all sorts of issues with coronavirus and economic policy and so forth. So that would suggest that your preferred candidate winning should be worth something like it's $1,000 per person, that would be $300 billion worth. So voting, you have a 1 in 10 million chance of your vote making a difference. We consider that the equivalent of buying a lottery ticket, but not a sort of lottery where if you win, you get rich. It's a sort of lottery where if you win this 1 in 10 million event, everybody in the country becomes a little bit happier. Not happier because their candidate wins, but everybody in the country has a better life because of the policy held by your preferred candidate. So in that sense, it's as rational to vote as it is to do all sorts of other altruistic acts. Some people have been brainwashed to believe that rationality and selfishness are synonyms. But as a political scientist, I can tell you rationality versus irrationality, or selfishness versus altruism, are two different dimensions in behavior. Of course, you can be rationally selfish by coming up with some clever way of scamming people on Wall Street. You can be irrationally selfish. You can do something that you think will benefit yourself, but actually you're not. Like, you can be a day trader and actually lose money because you're irrational, even though you're trying just to gain yourself. You can be irrational and altruistic. You can do something, you can make a supreme sacrifice that doesn't help anybody. Or you can be rational and altruistic. You can work for GiveWell, or you can vote, or you can do all sorts of things that put another brick into the wall of civilization in a way that is a rational use of your resources. So that's why it's rational to vote. Since this is the statistics department, let me just interject that what's the role of statistics in all of this? Well, obviously the key role was the probability of your vote being decisive. The probability has to be kind of order 1 in 10 million because there's 130 million voters. If all election outcomes were equally likely, that is, 130 million to 0, 129,999 to 1, 129,998 to 2, etc. If all those election outcomes are equally likely, then the probability of an exact tie is 1 out of 130 million. It's got to be higher than that on average because close elections are more common than landslides. So, and it can't be much less than 1 in 10. It can't be much better than 1 in 10 million if you think about the uncertainty of the election outcome itself. So that, and that's just order of magnitude calculation. We can do better, but I will tell you there are numbers in the literature by respected scholars saying that the probability of a tie election is 1 out of 10 to the 90th or 1 out of 10 to the 130th. Well, those are innumerate kinds of statements made by people like philosophers and economists and political scientists. Philosophers and economists and political scientists aren't always supposed to get the numbers right. They have other jobs, but that's where statisticians come in, and we're supposed to not only get the number right, but also explain why a probability of 10 to the minus 130th doesn't make sense. So I always say when I teach that, well, when we're training our students, that everyone with a statistics degree ends up becoming a teacher. Now, most of us don't become statistics professors, but wherever you work, you end up spending a lot of time teaching statistics. You always, in any consulting project or any real world project, the statistician always spends lots of time explaining to people what a probability really means and what a p-value is and all these other things. So I asked Jingyi what I should speak about today, and I pointed her to my published papers page, and she just picked the first 2 papers on the list. So that's what I'm going to talk about. I don't want to take up all the time because I'd like to answer questions and get into arguments and that sort of thing. So maybe you can put comments in the chat already, although I won't look at them now, but then we can have discussion later, or you can make a note. So please, while I'm speaking, think about what questions you might want to ask. And also let me say it's a pleasure to speak at UCLA. I have a lot of friends in Los Angeles. And in fact, I had been planning to visit with my kids a few months ago. We bought tickets and we were going to go see the Lakers play, actually, but then we weren't able to for coronavirus. So this is the best we can do. So my first paper that I'll discuss is comments on the paper Statistical Modeling the Two Cultures by Leo Breiman. So what happened here was that a statistics journal asked me and various other people to comment on this paper, the journal Observational Studies. So they had a plan that they're going to reprint this with discussion, and they invited a bunch of people, including me. And so that the link that was on the abstract was to my discussion of this paper. I'll talk briefly about this. Breiman was a statistician who was justly famous for coming up with many ideas which have become central to modern machine learning. So ideas such as stacking and bagging and classification and regression trees. He was involved in a lot of these ideas. Now these are very central to statistics and machine learning, but at the time he was doing that, they were more on the outside. And so he wrote this paper in 2001, contrasting 2 cultures, the traditional statistical culture of probability models with the predictive modeling approach that he did. And I guess the characteristic of probability models is that they kind of make sense, but they're oversimplifications. The characteristic of models such as classification trees and all these other models is that they don't really make a lot of sense, but they're highly over-parameterized. So the trick that made these methods work, there were kind of 2 tricks. Probably the most important thing was a kind of willingness to fit a model that makes no sense. Like just a kind of willingness to jump off the cliff and try something, which is a very kind of computational attitude. Let's see how it works. And even though first the models didn't really make sense, and second, there was very little, if any, theory underlying the model. So that was number one. Number two of what makes the models of Breiman and his successors so successful was the fact that they were over-parameterized. So more can easily have more parameters than data. As you get more data, you can fit more parameters. The fitting, the amount of complexity of the model is kind of defined by the fitting procedure itself. And then the third thing that made them work is regularization. And in old style CART modeling, regularization meant that you would fit only as much as you needed to, and you would use cross-validation to stop from overfitting. More modern machine learning methods, such as deep learning, use, well, what we would call strong priors, or penalty functions, to get stable parameter estimates. Now, what's interesting to me is that there's been a kind of convergence of these cultures. So you could say that when Breiman wrote about two different cultures, that was perhaps at the era when these two cultures were furthest apart. And I say this because using Bayesian methods, which are very strongly parametric and strongly model-based, are on one hand, the non-parametric approaches have used more and more regularization, which is like using stronger and stronger priors. And from the Bayesian point of view, we've been using more and more complicated models. So we can sometimes, when fitting Bayesian models, we will use techniques such as stacking, which Breiman invented in order to get more accurate predictions. And when people are fitting machine learning approaches, they often frame them Bayesianly, even if they're not getting a full posterior distribution, in order to get more stable estimates. So there's there are these dualities between computation and inference that conceptually, maybe there's no reason why stable computation should be connected to low variance inference, yet they often seem to go together. And we also have something we call the folk theorem of statistical computing, which is that when you have a problem with your computing, it often implies there's a problem with your model. Now, it doesn't have to be that way. Often, I mean, of course, in real life, you can fit models that are legitimately difficult to fit. They're legitimately multimodal distributions, which are hard to fit. But in my experience, typically when I have slow computation using any algorithm, it typically means that I need to rethink things. And I can talk about that for a moment. I didn't talk about the folk theorem in that particular paper, the folk theorem of statistical computing. But first, I'll give you a simple context. You're doing multiple regression, linear regression, or logistic regression. Nowadays, it's very stable, but old school, if you put yourself back 60 years ago or 70 years ago, if you're fitting linear regression and you have a near collinear design matrix, you can actually have problems. You could actually have problems with the computation. Now, what does it mean to have regression with a near collinear design matrix? Let me give you an example. Suppose I'm predicting presidential elections based on past, so I'm predicting national elections based on past economic conditions. And yeah, I have economic variables like unemployment, inflation, change in GDP, change in per capita income, consumer confidence. I run a regression. I might have, let's say, 16 past elections, and I have 8 economic variables, and they're highly correlated. So I have strong collinearity. Well, I mean, they really are close to collinear. It's a real issue. So in what sense do I mean that the computation problem implied a problem with the model? In the sense that I should not be having a flat prior on all these coefficients, that I actually have some prior information. Like, I don't know which of these economic conditions is more important than others, but I'm pretty sure that all other things being equal, more unemployment is going to be bad. All other things being equal, more economic growth is going to be good, more consumer confidence is going to be good, and so forth. Now, in that sense, there's a lot of ways to go. So we could fit a model where we just include fewer predictors. We could try several different models, each with one predictor or one or two predictors, and pick the one with the best cross-validation performance. We could include all the predictors, but constrain the coefficients to all be positive. We could fit up all the we could put we could average them. We could rescale the predictors so they're on standardized scale and put the mean of them in. We could put the mean of them in and then put the deviations, the separate predictors relative to the mean, but then give them strong priors to constrain the coefficients from being too far from zero. You can come up with a million ideas. Many of them are going to be similar, which is kind of what Leo Breiman might have said, that what's important is what you put into your model. This is actually Hal Stern's expression, that the most important thing about statistical analysis is not what you do with the data, it's what data go in. And maybe Breiman would add also what data you, also he might add how you might evaluate your method. So in my article, my short article about Breiman, I also talk about areas I disagree with him. I feel those disagreements have to do with there's a temporal interaction with time on that, which is that he was writing in 2001. He was not completely up. As all of us, we tend to be not completely aware of areas outside our own research. So his idea of what Bayesian statistics was about 40 years out of date. I don't think he recognized the convergence that was happening. I think it's often a risk we all have to dismiss ideas that we're not familiar with. We're often not familiar with the latest developments. And that's one reason it's good that there are all these applications, right? Like they built that machine that can play ping pong, right? That's super impressive. So I can't dismiss adversarial networks and deep learning because they can play ping pong, right? And it's hard to dismiss Bayesian methods because we actually use Bayesian methods to do survey inference and learn about state level opinion from national polls and so forth. So we have to be aware of that. But I do think it was a privilege or a pleasure to discuss Breiman's article and to see what he had anticipated and what he hadn't after 20 years. Okay, so that's number one. The second article that I was going to discuss is called Information, Incentives, and Goals in Election Forecasts. This was a fun article to write. The background is that I was contacted a few months ago by a data journalist for The Economist magazine, and they were preparing a presidential election forecast using state polls and other information. And he asked if I could help. So my collaborator, Merlin Heidemans, and I worked with Elliot Morris, who was the Economist data journalist, and we put together a model. And we had, I'll tell you briefly how the model worked, and then I'll tell you a couple stories. And then you can, of course, you can read the article on your own time if you haven't already. Our method put together several pieces of information, and I'm going to tell you the pieces of information and then say briefly how they went together. The first piece of information is a fundamentals-based forecast of the national vote. That's what I just told you about. It says basically in the 2020 context, the economy is not going well, the president is not popular, and he's running for re-election. So that's bad news. You put that all together, and we predicted that the challenger would get about 54% of the two-party vote, the challenger being Biden, but with an uncertainty of, I think it's like 54% plus or minus 3%, something like that, like quite a big uncertainty because, or maybe even plus or minus 4%. Obviously, these predictions, the economic conditions aren't perfect. It's a tricky model. We have a simplified version of this model in our book, Regression and Other Stories. The full model is complicated, not in a big data sense, but in a small data sense, because we don't have a lot of elections. I said that presidential popularity and the state of the economy are historically strong predictors of the election outcome, and they're also should be strong predictors of the election outcome. It's logical. There are many possible economic predictors, but here maybe I'd like to say that you'll expect these predictors to be stronger when the incumbent is running for president. So if Trump had stepped down and Mike Pence were running for president, I think the state of the economy would be less important because people don't judge the new candidate as strongly as they would judge the incumbent. In addition, we have more political polarization than we used to. I'm sure you've heard about this. So in 1984, Ronald Reagan was reelected president with 60% of the vote. It's hard to imagine anybody could get 60% of the vote right now, just because Democrats and Republicans are more, Democrats strongly hate Republicans and Republicans strongly hate Democrats. So polarization is not so much rooting for your team as rooting against the other team. Everybody else is like the Astros as far as you're concerned. So the model is kind of has to change over time. So it's not even as simple as fitting a regression. You have to put a lot of prior information in and structuring the model and having it make sense. Anyway, that's the first part of our model. It's a prediction, a forecast with uncertainty of the national election. The next part of our model is the relative positions of the 50 states. So from one election to the next, the relative positions don't shift much. So we take previous election results and we allow a certain amount of variation. So putting the national forecast and the relative positions of the state together, that gives us a prior distribution on the vector of 50 state outcomes. So it's actually a multivariate normal distribution or a multivariate t distribution or something like that, representing our prior before getting any poll data on how the election might occur. And our prior said that Biden was the favorite. Then we get polls. We get national polls and state polls. State polls are informative of public opinion at the time that the poll is conducted within each state. National polls are a measure of the public opinion nationally, which we can model as a weighted average of the 50 state opinions. We allow for sampling error. Obviously, each poll has a margin of error. We also allow for several sources of non-sampling error because surveys can be wrong. They are wrong. We allow independent survey error. We allow non-sampling error. We allow correlated non-sampling error. We allow non-sampling error that depends on the survey organization. And we have a special term of non-sampling error for surveys that don't adjust for party identification because there's some evidence that you can get systematic biases because surveys have too many Democrats or too many Republicans in them, even after adjusting for the other variables in the survey. Now we have one more part of our model. We need to tie things together. We have a prior for what's going to happen on election day, and we have polls which tell us which give us imperfect measures of public opinion today. And again, in our model, it's direct. We can include state and national polls because we model everything at the state. We modeled everything at the state level. So then in STAN, it's easy to just aggregate everything. Finally, we have a time series model allowing public opinion to shift over time. So when people, right now, we give Biden something like a 90% chance of winning the election. And when people ask me, why is it 90%? I say, our fundamentals-based forecasts predict Biden's going to get about 54% of the two-party vote. He's at about 54% in the polls. So it looks like he's the clear favorite. And then people say, okay, fine, but then why is it 90% not 100%? And I say, well, there are two reasons. First, the polls could be off, and second, public opinion can change during the next few weeks. So you don't know. Survey non-response rates are like 99%. So there can certainly be differential non-response that hasn't been anticipated. Now that's all setting aside like dirty tricks and polling places being closed and ballots being thrown out and legal challenges and stuff like that. It's all about public opinion. It's all about vote intention. So I haven't looked at anything else beyond that. Now let me, before kind of taking a breath and letting you ask questions or comment, I wanted to tell you a couple stories about this and how this paper came to be. So we created a forecast and it took us a few weeks. And the way we developed it was that we well, the fundamentals-based model is fit pretty much independently of the poll aggregation. So I spent my time helping with the poll aggregation part of the model. We had polls. We don't use raw data from surveys. We're only using reported poll numbers. We know when the poll was done and what state the poll was done in, or whether it was a national poll, and what organization did the poll, sample size, stuff like that. So we had data from 2008, 2012, and 2016. So in building the model, we didn't look at 2020. We just kept fitting it over and over again, playing with it to 2008, 2012, 2016, until we got reasonable results. As we started with a model, and then we fit it, and we looked at the model, and the model allowed the different states that they're all moving together. And I said, well, this isn't right. There can be changes during the campaign, like in 2016, where some states moved toward one candidate and others moved toward another. So we had to increase the amount of state level variation in the time series. And then we had some other problem where it seemed like it was taking the polls too seriously. And so we had to increase the non-sampling error in the polls. So there were, like, we kept doing things, like each time we were making the model better. It would be as if you're teaching a class and you get feedback from the students, and every time you get a little bit of feedback, you use that as an opportunity to improve what you're doing. Every time you do it, you have a reason. So we weren't blindly, it's not that we were like had a model with 80,000 tuning parameters and we were minimizing cross-validation error, which would be hard to do given that we only have 50 states and 3 elections. It's more that we were following this workflow where we kept looking for anomalies, and when we would find something that didn't make sense, we'd go back and look more carefully at our model. Then we thought it was reasonable. We liked it. We released it. After a few weeks, some people pointed out some issues. They weren't quite, people didn't quite believe certain predictions we were making. And then we went back and looked at the model, and we had some bugs in our code, and we also had conceptual errors. So we first determined that we didn't think that fixing the errors was going to have a big change on the predictions. So we spent about 2 weeks and fixed up our model and then updated it. Then meanwhile, we talked to people were pointing out other models out there, other election forecasts. So we decided to write a paper. And we published it in the journal Judgment and Decision Making, because they're a really cool journal. I contacted them and said, we have this. I contacted them in like mid-September and said, we have this paper, like I'd like to publish it before the election. Can you do that? And then they said, well, we have to review it, but we can do it fast. And if we like it, we can stick it in the September issue. So they did that, that was good. Like, publication is somewhat arbitrary, but I do feel for readers, if you can go to the trouble of publishing something in a journal, it makes readers' lives easier, because then they say, well, here's the journal. We can read other papers in the journal. If you publish it in an archive, they just have to take your word for it. So they can say, well, they like me. Oh, okay, that's fine. But like, maybe that's not enough. I collaborated on this paper with 3 wonderful colleagues. Jessica Holman is a computer scientist who does research on graphical perception and communication. Chris Vlasian is a political scientist who's worked on understanding election campaigns. He wrote a book a few years ago called The Timeline of Presidential Elections. And Elliot Morris is the data journalist at The Economist, who put a lot of this together. So then in our article, we talked about the information that went into the model, as I just told you. And then the fun part of the article, though, was the part about communication, where we talked about how do you communicate probabilities. So how do you say, we think Biden has a 90% chance of winning? How do you convey that without people thinking 90% is the same as 100%? How can you check your predictions, given that there's only one election? There's 50 state elections, but they're correlated. There's only one national election every 4 years. How can you possibly judge whether your predictions make sense? And also incentives for various pundits to have overconfident or underconfident predictions. And it was interesting to me that for some pundits, there's a real advantage to making overconfident predictions, because if you make an overconfident prediction, you get more attention. And we gave examples of in pundits in the 2016, we had one pundit who said that Trump was going to win in a landslide, which obviously he didn't win in a landslide in 2016. He got fewer votes than Clinton. And then another candidate, another pundit saying that Clinton had a 98% chance of winning in the Electoral College, which of course didn't happen either. But the pundits like just got more exposure after doing that. But then there's also incentives for underconfidence. So we looked at the inferences from the 538 website, which is a website that gives you a lot of, that produces an analytics and odds in a lot of different events in politics and sports. And they had reported some of their calibration studies, and it turned out that their uncertainty statements in sports were calibrated, but their uncertainty statements in politics were systematically underconfident. They make their political intervals too wide. And we conjecture that their utility function is that for sports, they kind of want to get things right because they're dealing with a bunch of sophisticated sports bettors. But when it comes to politics, they have an incentive to make their intervals wider. So one way of thinking about this is forget about 95%. I'm about to stop, by the way. One way to think about this is to forget about 95% intervals and think about 50% intervals. What if your only job in life were to produce 50% intervals? Well, as a statistician, I'll say that I want 50% of my 50% intervals to contain the true value. No, that's not enough. I mean, obviously, you can get perfect coverage with completely noisy intervals. So if you flip a coin and half the time you give an interval of 0, 0, and half the time you give an interval of minus infinity, infinity, you'll have 50% coverage, but that's not what I'm talking about. You obviously want intervals that are as narrow as they can be while still having expected coverage that's correct. If you are a pundit, though, it might be different. So if I give 50% intervals, when the truth is outside the interval, I look like I got it wrong. And when the truth is inside the interval, it looks like I got it right. So there might be an incentive for your 50% intervals to contain the truth about 70% of the time. So you're outside, the truth is outside the intervals enough time to give you some sort of people realize you shouldn't always include it, but at least you're right more often than you're wrong. So it's like a lot of things. You have to see what the incentives are. There's no reason why the incentives should favor calibrated probability distributions. The incentives are what they are. So it's very interesting for us to think about that because our own intervals itself have problems. Someone recently went back to our model fit to 2008, 2012, and 2016 and looked and found that there were a few states where the outcome was outside of our 99.99%, outside our 99.9% interval. That shouldn't happen very often. It happened like a few times out of 150 elections. I think our tails of our intervals are too short. But we got that wrong because in all of our checking of their model and all of our fitting, we had focused so much on swing states and getting the swing states right, conveying the information in the polls, not getting the national election wrong. And the largest errors tended to be in non-swing states where there's not a lot of polling and like in some sense, who cares? Okay, so who cares that Barack Obama got 3 percentage points more, 3% more of the vote in Hawaii than he was expected to get. He was going to win Hawaii anyway, but that's part of our model. And so we did find problems. So we could, having done the forecast ourselves, made us very aware of these issues. And it really made the paper a lot of fun to write because we could kind of roast ourselves a little bit too. So at this point, I'll stop. I don't think I have a theme for the different parts of the talk, but I'm happy to answer any questions that people have.
There's one question in the chat box about the Bayesian credible interval interpretation.
So, I see. From Kan Sheng Ho in the chat box. Yeah. So my response is that the Bayesian predictive interval should have the correct coverage on average if you integrate over the prior. So actually, I wrote a post on this a few years ago, I think, or maybe even more recently, that called Bayesian inference is frequentist. That Bayesian inference is optimal, has optimal frequency properties if you integrate over the prior. I mean, this is not a secret. This is well known. Right? So the prior distribution in Bayesian inference has the exact same role as the reference set in frequentist inference. And so all the strengths and all the weaknesses. That is, it really should be true on average that you have the right coverage if the model is correct, which is true of frequentist inference also. And it also has the other issue that just because it's correct on average, it doesn't mean it's right in any given case. It's just probabilistic. But I do think that we can evaluate these things in a frequentist way, at least in theory. The practical difficulty is that you don't have a lot of independent observations. So we only have, so in 538 website listed hundreds of thousands of their political forecasts, and they looked at their coverage, but it's not really hundreds of thousands of forecasts because they have forecasts from 50 states in each election, and they have states for they have multiple forecasts for each day. They just, every time they reran their model, they saved it on the computer. So it's like hundreds of thousands of very highly correlated outcomes. So you can't really, but nonetheless, that all said, you can sometimes learn that you're uncalibrated. It's like a lot of things in life. You can't prove that you're right, but you can often find where you're wrong. So anyone?
Sorry. I guess a related question is, how should general public interpret those predictions from the different models? Or maybe I wonder how they are useful for their perception of the election.
I think, I don't know, I kind of think we should not, we should, when in doubt, we should be more technical. Like, I don't want to do something wrong because I'm afraid that someone's going to misinterpret. It's kind of my job to get the numbers right. So that's the only thing. And I feel it's the same way like with the 538 people when they're doing the sports betting. Like maybe sports betting can be bad. Some people are gambling addicts. Should they not do it? It's like, well, that's not their job. They're trying to get the numbers right. So that's kind of like, I'm interested in communication, and you can read what we wrote about it in the paper. I mean, there is a lot of literature from psychology favoring what's called natural frequencies. So you're not supposed to say that there's a 2% chance you'll have this disease. You're supposed to say, if you're 100 people in this room, 2 out of the 100 people would have it, right? Like that's how you're supposed to think about things. And I kind of believe that. Because as I say, it makes sense and there's research. It's not always clear how to do that. So for an election, what do you can say, if we held the election 10 times, then 9 times out of 10 Biden would win. That's kind of weird. Sometimes what I say to explain 90% is I say, let's go back 10 elections. That's 40 years. So 40 years ago was 1980. In 1980, Jimmy Carter was running against Ronald Reagan, and the election was considered to be very close. But then Reagan won by a lot. So I like to say, okay, that's an example. Every 10 years, you can have a surprise like 1980. 1980 wasn't the world's biggest surprise. Reagan was kind of ahead. He was expected to win, but not by so much, right? So like things can happen. That was also a less polarized era. But so I tried to use this natural frequency idea as much as I can. I guess that's my answer to your question.
Thank you. And there's another question in the chat box.
Let's see. Let me open the chat box here. Oh, 538 deluxe model. That's so tacky. There's just one model. There's no deluxe model. It's like your deluxe model, like your deluxe model is your model, right? Like what's the point of the crappy model then? That's silly. Okay, yeah, we wrote about this in our paper. That you can, the difference between 75% and 90% is not very much. So let's suppose we approximate the predictive distribution by a normal. I mean, it's not exactly, but for the purpose of forecasting the winner, that's roughly right. Okay. So our estimate and standard error for Biden's share of the two-party vote is approximately 54% plus or minus 2%, which means we have roughly a 97.5% chance of Biden winning the popular vote. It's only 90% for the electoral college, because to win the electoral college, Biden has to win probably has to win more than half the vote. Anyway, here's the point. Our forecast is approximately 54% plus or minus 2%. Theirs is approximately 53% plus or minus 3%. So their fundamentals-based model is a little is their model based on the prediction based on the fundamentals says it should be close to 50-50. Our fundamentals prediction had Biden clearly like in the lead. They didn't. Now, are they right or are we right? What can I say? Like, we don't have enough data to evaluate. Like, our best judgment is, yeah, this year the economic and political conditions favor the challenger, but like a lot depends on how you count the economic conditions today, given there's coronavirus, and like, how do you think about that? They made different judgments than we did, but you have to make judgments. We also made judgments about polarization. So we argue, we put in our model, we say that economic and political conditions are less predictive than they used to be. And because of polarization, in one of the descriptions, the 538 model, they said they calibrated it to elections back to 1860 or something. Well, I don't know. I don't really think 1860 is very relevant, but like, that's their call, right? So first, we have a different fundamentals-based forecast than they do. It's just the way it is. So then they have a larger uncertainty because they basically added uncertainty to their model. They basically said, we're a little worried. This has to do with this incentives issue, that they flat out said that they want conservative predictions, and conservative means that your intervals are wider. But what I guess I'm like, I like what we did. Like, it seems reasonable, although as I said, it has some problems in the tails, but I can't really defend it so much beyond saying like it made sense to us. Like, you can't really empirically distinguish between 54 plus or minus 2 and 53 plus or minus 3, but they give much different probability. The probabilities look much different. But so that's where it's coming from. But it'd be hard for me to argue that we're right and they're wrong. It's just like we're making different choices. It would be, and I mean, it would be like, to continue the sports analogies, like you could have two teams having different strategies of, how they do their lineup, but it's really, you don't have enough data to really evaluate. Let's see, someone said, can you talk about what changes you might make to the economist model if pollsters regularly released raw data? Yeah, if they had raw data, you'd want to model it all. I mean, you'd throw all the data in for the big MRP model, get better estimates for opinion in each state. I mean, I sort of glad that they're not doing it, because that would be so much more work, but that's kind of the next frontier. Like, you could also look at changes, demographic-based changes. So we're doing everything by state, but you could see, are there certain swings where certain candidates are becoming more or less popular among white people, or less educated people, or religious people? There's so much you can do. And we've done a lot of it over the years. It's surprisingly hard, though. I found something as simple. We did a project a few years ago. We were estimating public opinion, like vote preference based on demographics from some we used surveys from YouGov, where we had the raw data, tons of data. We thought, well, let's just start by estimating something simple, the gender gap as it varies by state. It was very hard to estimate the gender gap by state. The gender gap meaning the difference between how men and women vote. How could the gender gap be hard to estimate? Well, first, within each state, of course, you have a smaller sample, so it's more model-based, but it's really about non-response. Like, if you could look at the raw gender gap, but what if one survey what if surveys are consistently oversampling Black women, but not white women? Right? Then you're gonna, if you have any convolution with ethnicity, it's going to destroy your results, because Blacks and whites vote so differently. Well, you can adjust for that, but then there are other variables. So the results are so sensitive to what you adjust for. It's surprisingly difficult. Do I think the forecast itself can affect the election results? I don't really think so, but like people have argued about that. I wrote something, I blogged something about it. There's a paper we discuss in our paper. We discuss this. We discuss an article by Westwood et al. Um, and there was a discussion. I guess if you Google our blog and then look for like Westwood, like you'll find our discussion. There's a bit of debate about that, but it's hard to say. Why were many forecasts in 2016 so wrong? So we wrote an article. I wrote an article with Julia Azari called 19 Things We Learned from the 2016 election. Forecasts in 2016 were wrong for a couple reasons. One was that they relied too strongly on state polls. Like people hadn't really done a good job of integrating state and national polls. Like we can do that with our STAN model, but it's hard. It's somehow hard to do if you just do poll aggregation. So it was easier for people. There was a tendency for people to just use state polls. And then the trouble was that the polls in certain Midwestern states had not adjusted for education, and there was non-response bias based on education. Also, that when you're using the state polls, you have to allow that the polls can be wrong, and that that these errors are not independent. And so people, I think, weren't accounting for the possible correlations enough. Now, what could go wrong this time is a natural question, and what could go wrong could be something else, some other kind of non-response that hasn't been adjusted for. Richard Border, read some of the points in the first row. When teaching Bayesian statistics, what should you emphasize about the role of priors? I've kind of gone around and around about this. So when we first wrote the first edition of Bayesian data analysis many years ago, 25 years ago, we had what we sometimes now call the Bayesian cringe. So we kind of had a lot of very weak priors, non-informative priors. We emphasized that prior didn't matter that much. I think more and more I'm working on problems with either complicated models or small data sets where the prior is more important. I don't like the term prior belief. I like the term model or prior assumption. So the prior is a model. It's an assumption that you put in. So you put in assumptions and you get stuff out of it. I don't necessarily believe it. Like it's like, what if I use the normal distribution? Or what if I do logistic regression and I use the logistic transformation? Do I believe in the logit? Like, do I believe that the data are normally distributed? Do I believe that there's additivity and linearity? No, I don't believe those. Those are assumptions I make in order to, they're regularizations. They're assumptions I make in order to get stable estimates. And as Breiman et al. Have taught us, there are lots of ways of making assumptions. You can make assumptions using a parametric form, or you can make assumptions by using a non-parametric model and then controlling the estimates to be stable. There was a question, Mark Hancock, how the two cultures debate relates to departmental history and small sample statistics. I can just tell you a story about this, which was that like I did not get along with Breiman. I think I only met him like twice, even though we were both at the University of California at Berkeley. But once they had PhD qualifying exam. Now, I hate the PhD qualifying exam, and a lot of universities don't do it anymore. But at the time, like we were asked to write questions. So I wrote a question and I had data for 3 elections. I said, create a model to predict 1990 from 1990 from 19 oh so create a model to predict 1988 from 1986 and then critique that model and then use the model to predict 1990 from 1988 and then critique it again. And the idea was first supposed to be that there's various nonlinearity and stuff you have to put in the model or else critique it. And then the second point was that predicting 1990 from 1988, it's not the same as like there could be a national error term that you need to adjust for. Anyway, I had ideas about it. So it was, and I gave it to them. Then I saw it wasn't on the exam. So Breiman was in charge of the exam. So I asked him what was up and he said, oh, we don't like modeling here. So, so I said, can you just change the word model to predict? But he didn't want to do it. So he, like, I think he had very strong feelings that he just didn't like models anyway. But that's like, you know, that's okay. I mean, I think that's like part of the story. It's like people have their irrationalities, but that doesn't mean their arguments are wrong. That just means that's why they're passionate about these things in the first place. So I think he had a personal issue for whatever reason of not liking models, and that inspired him. People are inspired to do all sorts of great work because they have like a, you know, a bug up their butt like that. I'm sure
I
it's
just had
true of us too.
I just had one brief comment to that, and this is there's a lot of graduate students in the audience. The founder of our department, Jan de Leo, came from the European school, which probably doesn't get as much play clearly here because, you know, of the differences. But the European school were data analytic in Breiman's sense, you know, and what they were really interested in is understanding structure from data and getting models out of the picture. So my question here is sort of interesting. They did things like correspondence analysis, which were mathematical models for data without, you know, having an data generating process in mind, just to describe the structure of individual data sets. So firstly, that's of interest to the students to know that history, but I'm also interested to know whether you think that particular perspective on it, where that fits within the two cultures debate.
Well, I think there are connections. So one thing that I've written about is that, well, here's another thing that, so different from what Breiman did. So let's say Breiman's associated with like advanced, you know, all this great stuff machine learning is done. And let's say that I'm associated with parametric modeling, basically. So like small data sets, lots of models in order to get predictions and all that, like handcrafted models. There's another tradition in statistics which is different from both of those, which is Tukey's exploratory data analysis. So I've argued that exploratory data analysis and of course correspondence analysis has connections to things like EDA. And I guess I've argued that EDA is actually connected to models in the sense that EDA is seeing patterns that weren't expected in the data, but if something wasn't expected in the data, then that must mean you had some expectations coming into it. And so I remember years ago talking with the great Bill Cleveland, and he had some data, there was some data set, and I was trying to follow Tukey's principles. So I said, well, Tukey would say you should first like make fit, you know, he had like in EDA, he talked about additive models. So subtract this, then look at the residuals, then transform the residuals. And like, you know, he did his spectral analysis where he did like the transformation of the transformation. Like the guy was like a maniac, right? Like did like just, you could not leave the data alone. And so I mentioned this to Cleveland, and Cleveland said that Cleveland said that he used to think that way, but now he's this was many years ago, but when he said he thinks he just likes to see the data as is. So Cleveland argued that if you really plot the data carefully, you can see a lot of these patterns without even needing to subtract. But you know, I think that's maybe some of that's a matter of taste, like where you draw the line. But yeah, I agree with your kind of larger point that we shouldn't think that whatever Breiman did and whatever I did represent two poles or the only two things that you can do or anything like that. There's completely different ideas out there too.
And I want to add a point following Mark's comment about a small sample size. I think practically sometimes people have to assume a simple model because of their sample size is too small. It's just a practical solution.
Well, you don't have to, right? I mean, because you can always have a complicated model with very strong priors or very strong regularization. Like, I mean,
Yeah.
but yeah, I mean, there's the limit to what you can learn. I mean, it depends. So I do some work in pharmacology, and there you can have small number of data points, but you just have a very strong model, like a differential equation model, like telling the whole story. And Yeah, I mean, there's so many. We did some a few years ago, we were reconstructing climate from tree rings, and it was very difficult. Like, I mean, pretty much, we actually like got a grant, we published a paper, but I think the main thing I learned is how hard it was to do that, because you need like a lot of trees to try to draw this, because it's an ill-posed inverse problem, reconstructing things from the trees that you have. So there aren't really a lot of really old trees that they have data on. But then the transfer function really differs from tree to tree. So to estimate it, you need more trees. But once you get more trees, the model has to get more complicated. Meanwhile, you have more trees and the model's more complicated. And it's already nonlinear and it's already slow. So then it becomes too slow to run. What do you do when a model is too slow to run? You break up the data into little parts and fit it separately to each data point. Well, but then you don't have enough data. So it's like I never felt that we were at a comfortable plateau. Like with the, the election forecasts, I feel like, oh, we're kind of at a plateau. We're where we are. Maybe we could do better. 2020 is a pretty easy election to forecast because Biden is doing so well. Like, so there's kind of less pressure on the forecaster. But sometimes we have problems like the tree ring where I just feel like we're never there. It's very frustrating.
There's three new questions.
Our election forecasts getting better. I mean, it's just an arms race. Like we're getting better, the data are getting worse. Like you have more data. I think, probably the people who care most about election forecasts are not news organizations, they're campaigns, and they're trying to figure out who they should be trying to get to vote. And so like in some ways, I think there's a lot more technology and people can do a lot more, but then again, survey response rates are lower than ever. So there's continuing challenges. Is the model getting less uncertain as there are several million votes already cast? Well, first, our model doesn't know about that. Like, so our model only has these fundamentals in the polls. And so in fact, there could be a major news event tomorrow, but it wouldn't change our model until it percolated through the polls. We just wouldn't, like, our model wouldn't know about it. It would just be sitting there, like you waiting for something to happen. We don't account for the votes already cast. It's not clear how you should account for the votes already cast. There's still a small proportion of the total, and we don't completely know who they were for, although we know something about that. There's information there. I'm not really sure what to do with it, though. How do we know if our forecasts are getting better? You can know if you're in a situation where you can make like richer forecasts. Like, so for example, if you're forecasting earthquakes and they say, well, when's the big one going to hit LA, right? Well, like, what are we going to do? Like, but if I can also forecast lots of little earthquakes and say, well, I'm getting good at that, then maybe you're getting, that's not me talking. Oh, okay. So yeah, anyway, we can forecast 50 states. So that's better than forecasting the whole country. What about state legislative elections? Well, you should be able to do it. So I haven't done anything but help this guy with the presidential forecast. I think they have a forecast for Congress. I haven't even looked at it. I have no idea what's in their forecast for Congress. They did that on their own. So if you want to really want to see if your forecasts are getting better, you should be forecasting local elections, because then you have a lot more data. And we have surveys. I mean, all these state polls, they ask people, who are you going to vote for locally? Like, it's not like, it should be possible to do. It just takes effort. So it's 3, it's 2, it's noon for you. So I guess I'm probably supposed to stop anyway. I mean, I'm happy to answer any other questions people have.
Yeah, so for the audience, if you have questions, maybe you can just unmute yourself and ask the question. There's another question asked by...
isn't using surveys? No, when I say using surveys to build a forecast, I mean, you evaluate the surveys on the election. I'm just saying, if you forecast more elections, you can do better. That's all.
You kind of spoke to this question a little bit earlier when someone asked about whether you think that models might or forecasts might actually affect the results of the election. Are you at all, do you think that that might have happened in some part in 2016? If not necessarily the models, then at least the way that people were talking about the chances that someone would or wouldn't win? And do you think that that's at all, well, one, was it a discussion that you had internally about whether to do this at all? And if not, do you think that that's
So
similar to the discussion?
I don't know. In 2016, there was a lot of awareness of problems with the polls. And it's funny, I was actually, for the New York Times did something where they had a poll in Florida and they sent it to a bunch of people, including me and some colleagues, and I analyzed the data and we found Trump was ahead in Florida and all the other analysts said that Clinton was ahead because we're the only people who adjust for partisanship. But then I kind of forgot about that. Like then when the election was coming up, I was like, well, everybody seems to think Clinton's going to win. Like here are all the state polls. I think if I want to say there was a statistical error we made, like say not adjusting for things, but like in some sense, the statistical error we made was a kind of sensitivity analysis. Like we weren't thinking, well, our inferences are pretty sensitive to certain state polls. If we had maybe people had incorporated, that's why when we went back and fit our model to 2016, we ended up with Clinton having something like a 2/3 chance of winning, which is kind of, I think, reasonable. Like given the information right before the election, I think that would be a fair estimate. I think like there was kind of some bad luck, like the polling errors, you couldn't have anticipated the direction of the polling errors ahead of time. So the polling errors were large and had certain direction that was unfortunate for her. And then there were perhaps some last minute swings, et cetera. Like somehow that seemed kind of reasonable. But yeah, that level of certainty wasn't, that wasn't appropriate. But it's hard, like it's again, it's hard to know what to make of things. Like, this election looks a lot like 1992. Like it wasn't very close, but like you couldn't be sure. Like it was also similar in that Bill Clinton was a challenger, but as of 1991, George H.W. Bush had been very popular. So it's still kind of hard for people to believe that Clinton would win. Like, so this has a similar feeling. It doesn't mean it's going to happen that way. It just has a kind of feeling like that. And indeed, whenever a challenger wins, like 1980 is like that too. Whenever a challenger wins, like you're always kind of thinking, oh, is Reagan really going to pull it off? Like, so those are like these aspects of the story. So one thing I said, because people were, a few months ago, we were saying Biden had an 85% chance of winning or whatever it was. And people were saying, I got someone saying, well, I think he thought it was 50-50. I was like, what do you mean? He said, well, you just don't know what's going to happen. So I think that they were overweighting 2016. Say, well, 2000, no, it could be wrong, but things happen. Again, I said like every 10 elections, a 1 in 10 thing happens. And so like, that's where also, if like things happen a certain way, then I'll look bad and then I'll wish I'd had a wider interval. What can you say, right? You don't like, you don't really like, that's why as a statistician, you don't want to be so much in the business of making predictions. You really want to be in the business of making methods and evaluating your methods.
So given the discussion, I just wonder whether it makes more sense for us to just report that 53 plus minus 2% and 52 plus minus 3%, as opposed to giving a probability of winning, because that probability can differ quite a lot.
Yeah, I mean, sure. Like we do both. So like on our page, we have a distribution of and 538 people do also, right? So we have a distribution of electoral college outcomes. We have a distribution of popular vote. I think it's good to give more things. So for example, 538, like they have a distribution. If you go to their distribution for their estimate for California, you're going to laugh because they think there's a chance that Trump's going to win California. Now, like that's wrong. I don't think that makes sense. But like first, like who am I to say? Like, whatever. But it's good that they're doing that. Like they're putting it out there, and then you can say that's wrong. There's a problem with their model. It's good to know there's a problem with their model, right? So I think it's better to make more predictions. like be wrong in more ways. I mean, my own experience, like I years ago in 2008, I had this another story, which I allude to, although don't tell the whole thing in an article, that I had maps of how people would vote based on different income levels by doing MRP on survey data when we were writing our red state, blue state book. And they made these maps showing how people would vote, like how rich people would have voted, how middle income people would have voted, how poor people would have voted. And it was cool. And then people were asking about white voters. So I had this analysis I'd done of all the voters. I did another analysis of just the white voters, fit the same model. And something like 80% of the survey respondents are white, so you can fit it. I couldn't fit the model for minorities because with only 20%, I wouldn't have enough data to just fit it so well, but I fit it to the whites. And then I showed the maps and I put them online. And then someone I'd never heard of attacked me. He's like, these are wrong. And he was right. Like I had one state where if you look at how white people vote and you look at how everybody else voted, it would have been like 108% of black people voted for Barack Obama. Like it can't be more than 100%, right? Like, so what went wrong? Well, what wrong is I fit one model to everybody and one model just to the white people, but they were two different models. They did partial pooling and all sorts of stuff. They did different amounts of adjustments. And the result was that they weren't really consistent with each other. So I had to fit them. I decided if I really want to look at white people, I have to model everybody else, but then I can't cheat. I can't just fit the model separately to everybody else. I need to fit a model including ethnicity as a predictor in the model and include interactions. And so we did that. And it took a lot of effort to do, but it was all because I put these maps out there. So you put something out there that people can relate to. It's really great if you can then like get them, like people can then do you a favor of pointing out the problems. So we did the 538 people a favor of saying, well, I don't believe this California thing. Oh, they can decide what to do with it. That's why does our California forecast differ from 538's? It's based on national, state poll. Well, basically, no matter how you slice it, California, not only based on the polls, but based on previous elections, it's currently a very Democratic leaning state. The 538, I'm not sure because their code is not available. Yeah, it's the predictions. It is not just that the predictions do differ. Part of it's a presentation difference, but if you look at their page, they actually have Trump winning California as one of the possibilities. It's because I can't be sure because it's not, their code is secret, but I think that they added an independent long-tailed error to each state. And so then they have a small probability of a really big error. But it's like all things can happen. But I think put it this way, if Trump wins California, I think he's going to win all or almost all the other 49 states, which their model doesn't have. So I think they just kind of messed up. Like we messed up too sometimes. Because these models have a lot of moving parts. And I think that they were concerned about unexpected things happening. And so like I told you, our tails are too short. So they wanted their tails to be bigger and then they kind of overdid it. And then they probably didn't really look too carefully at it. And then by the time it's out there, people are looking, then it's kind of embarrassing and then maybe they don't want to fix it. Or it's this asymmetrical error. Like the loss function is if they make super wide intervals and people say, well, that's super wide, then that just fits into their feeling that they're conservative, which is like part of where they want to be. So they're not aiming for that kind of calibration there. But that's okay. They don't have to. You know.
There's one more question from Richard.
No, I just 536. No, I just answered that one.
Oh. So maybe I can ask one last question from maybe thinking from a student's perspective. So given what has been said about the two cultures, so for a graduate student, when you reach a problem, when you start working on a problem, how would you like find a balance, or which culture would you choose for that specific problem, given that you don't have so much experience?
I think you should be open-minded and multilingual.
Mm-hmm.
So, work on different things and And you'll end up working more deeply in some areas than others, but you shouldn't be closed to other options.
Mhm. Yeah, especially that different fields have different preferences for their modeling. But I think we shouldn't actually be limited to those frequently used models.
Yeah, it's sometimes just a matter of taste also. Some
Mm,
people I kind of like continuous models, and some people kind of like discrete models.
mm. Yeah, maybe that's the most difficult thing to get a taste for yourself.
It's like learning a foreign language. You
Yeah,
get that, you know.
yeah. Yeah, I think maybe a take-home message for our graduate students from today is that they will feel the subjectiveness of statistics.
Yeah,
Yeah.
perhaps we shouldn't try to make things look more authoritative than they really are.
Mhm.
And if we can be open source and like we can engage the community, then there are, you know, more ways that our problems can be found, and then we can do better than we would have done individually.
Yeah. Yeah, thank you so much for your comments. And there's another question from Adam. When do you use a standard model logic versus a first principles model like the golf one?
Yeah, I don't, it came up just today in a consulting project. I guess we usually try to do the easy thing first. So,
Mm,
you know, minimize the human effort. But there's a saying that it's harder to do the wrong thing right than to do the right thing right. So like sometimes you do find yourself contorting yourself. Like at some point, it's just build it from scratch can be easier. But I put something in regression, other stories about this. So we have, it's like there's so much in this book that's the trouble, is like there's so much I love in this book that like it gets lost because it's like in the middle of chapter 14 or something. But we're doing logistic regression, and when I teach, I like to give this example of things that the exam where the multiple choice exam with guessing, because then the probability doesn't go from 0 to 1, it goes from 1/4 to 1, so that's not logistic. Or things where the probability goes up and then goes back down. It's like even within something like logistic regression, you can go beyond it. And so it is like, and it is, I have seen, you do see people just trying to contort a conventional model to do what they want. I mean, you see stuff like people take data and they'll discretize the data just so they can do a chi-squared test, or they'll do regression discontinuity analysis, which is like probably almost always a bad idea, or they'll fit logistic regression on data which can't really go all the way to 0, can't go all the way to 1. So at least we tried to give an example. So there, I guess my point is there's something intermediate. Like you can start with the standard model and then you can add features to it. It's not completely first principles. First principles models, as in the golf example, they're crude also. So they're not, in some way, they're not that different from each other.
Okay, so if there are no more questions, let's thank Dr. Gelman for the insightful comments for today. And we really appreciate it.
It was great to see you all, or those of you all who I could see. So have a great day.
You too. Have a great day. Bye.
Bye.
Bye.